Hello, welcome to the first part of this lesson on equilibrium and how to use the concept of equilibrium to help us solve problems. In part 1, we'll start very quickly by going over the background knowledge you should already have, which you will need to understand the rest of the lesson. Then we'll talk about the concepts of translational equilibrium and rotational equilibrium and why they're useful for solving problems. Then we'll do some problems. First one is a very common one, mass hanging on two ropes. Ropes make the same angle with the vertical. How do you get the tension in the ropes? Problem 2, very similar, but the ropes are at different angles. That's part 1. In part 2, separate video, we'll simply continue with more problems. Problem 3, another very common type of problem, a beam supported at 2 points with a load. It could be a bridge supported at 2 points with a car in it, for example. How do you get the force on the bridge from the supports? Problem 4, typical problem you can come across, object is about to slip on a horizontal surface because it's being pulled sideways by a force at an angle to the horizontal. How do you get the coefficient of friction? Problem 5 is very similar, except the object is moving on an inclined plane. And the last problem is a rather harder one if you feel you want a bit of intellectual challenge. It's about a ladder resting against a wall. How do you get the angle at which the ladder would just start to slip down? Okay, as always, you'll need a pen, paper and calculator to get the most out of this. Remember, if you do things for yourself, you'll learn 10 times more than just watching someone else do it. So if you want to pause and get your pen, paper and calculator, now is a good time. Let's make a start. Required background, what you already should know to be able to understand this lesson. You need to know about vectors, how to add them, how to use components. I've put 3 stars by that. We're going to be using components a lot, so you need to be very comfortable with resolving a vector into components. You need to know about moments or torques, how to use the principle of moments in calculations. The formula moment tau is Ft sine theta. You need to know about weight, centre of mass, centre of gravity, normal contact force, friction, coefficient of friction. Now there are lessons on all of these topics and I'm assuming you are already reasonably comfortable with them. Let's make a start and talk about this thing called translational equilibrium. Well, here's a simple setup. We've got an object box with 4 forces on it. This box is in equilibrium because if you look carefully, 12 newtons to the left will be cancelled by 12 newtons to the right, 15 up cancelled by 15 down. The resultant, the total force, vector sum of those 4 forces, is 0. And if the 0 force or the resultant is 0, we can say this. The object's centre of mass must be stationary or moving at a constant velocity. And students can understand usually why this object can be stationary, there's no force on it, but it could also be moving at a constant velocity and still have 0 resultant. That's important. If the resultant wasn't 0, the object would accelerate, so it wouldn't be moving at constant velocity. So what do we mean by translational equilibrium? Well, translate means to move in a straight line without rotation. For example, the pentagon is translated. And if an object is in this state we call translational equilibrium, it means its centre of mass is stationary, or its centre of mass is moving in a straight line with a constant speed. So its centre of mass would have a constant velocity, which means 0 acceleration. And that's what we mean by translational equilibrium, something that's stationary or moving with constant velocity, or centre of mass is doing this. And the important thing which lets us use this to solve problems is that the resultant force on an object in translational equilibrium is 0, and it works the other way around as well. If the object is in equilibrium, the resultant force on it must be 0. Let's look at that in a little more detail with some true or false questions. Here's 3 questions. I'm not going to read them out. You can pause the video, read them for yourself, and decide if each statement is true or false. So pause the video and do that now. Well, I hope you've tried that for yourself. Let's go through them. Box resting on a table is in translation equilibrium. Yes, it's true. The box is not moving. Its centre of mass is not moving. So it's a true statement. A skydiver falling at a steady speed, so-called terminal velocity, vertically downwards, is in translational equilibrium. Well, it's a steady speed and it's in a straight line because it says vertically downwards, so it's a constant velocity. So that is also a state of translational equilibrium. It's a true statement. There are forces on the skydiver, but their weight is pulling them down, but that's exactly balanced by the drag, the air resistance, upwards. So the resultant is 0. And the last one, well, I hope you can tell it's false, because it tells you it's accelerating. The stone is picking up speed. It hasn't got a constant velocity. It's not in translational equilibrium. Here's another situation where we have 3 forces. Let's imagine these 3 forces, F1, F2 and F3, add up to give us a 0 resultant. So we know the resultant is 0. The important point you need to be aware of, because you're going to use it, is this. If the resultant is 0, the components of the forces along any direction add up to 0. Let me say that again. If the resultant is 0, the components of the forces along any direction add up to 0. Let me show you what that means. Let's pick a random direction. That purple line, I could have drawn it at any angle. I've drawn it as shown. Let's mark the angles between the force and the direction of the purple line. F1 makes an angle of A, F2 makes an angle of B to the purple line, and F3 makes an angle of C to the purple line. Now, from your knowledge of resolving forces into components, I hope you can work out what the component of each of those forces is along the direction of the purple line. Because the forces add up to 0, the components along the line add up to 0. The components acting upwards along the purple line will equal the components acting downwards along the purple line. Let me write the relevant equation. The magnitude of F1 times cos A is the component of F1 along that purple line and upwards. Similarly, on the diagram, the magnitude of F2 times cos B is the component of F2 upwards along the purple line. And that must be balanced by the component of F3 downwards along the purple line. That's F3 cos C. So we've got this equation, and that's a very important equation. That illustrates the statement that if the resultant is 0, the components along any direction add up to 0. That equation must be true. In fact, when we write the equation, and we'll often be using this technique of balancing components in different directions, we'd write it like that. We wouldn't bother with the magnitude symbol. We'd simply write F1 cos A plus F2 cos B equals F3 cos C for neatness. And you have to use a bit of insight to realise that that equation is basically the first equation without the magnitude symbols. Okay, that's translational equilibrium. Let's talk about this thing called rotational equilibrium. Well, rotate means to spin. There's something rotating. An object is in a state of rotational equilibrium when it's not rotating, or if its speed of rotation is constant and its axis of rotation has a fixed direction. Now that's a rather tricky concept, and we're not going to need the second part, so I'm not going to dwell on it. The key for you is to remember that if it's not rotating, it's in rotational equilibrium. And what can we say about an object in rotational equilibrium? Well, if an object is in rotational equilibrium, the total moment or total torque on the object about any point is zero. Because it's not rotating about any point. It's not rotating about the middle, not rotating about the corner, not rotating about some other point outside it. So we've discussed this in the lesson on the principle of moments, but let's just remind you that if it's in rotational equilibrium, the total moment about any point you want to choose is zero. That's very useful. That helps us solve problems. So, try these. Let me put 3 true or false questions up for you. Pause the video, read through them and decide if each of those statements is true or false. Pause now. Well, I hope you've tried them. The first one, well, if it's just resting on a table, it's not moving at all, it's certainly in rotational equilibrium. This one is a ball rolling at a steady speed, and its axis is horizontal. Is it in rotational equilibrium? Yes, it is. That's a true statement. If it's rolling at a steady speed, its rate of rotation is constant. And if its axis remains horizontal, maybe pointing east to west, then that's a fixed direction. The wording's not absolutely unambiguous, but it's meant to be a fixed direction of an axis. It's a true statement. And the last one is false because it's slowing down while it spins. Its centre of mass is fixed. Its centre is on the axis, but the speed of rotation is reducing. That requires a torque to make it happen, perhaps caused by friction. And that is a false statement. Okay, sometimes you're told an object is in equilibrium, or you want to say an object is in equilibrium. What does it mean? It means the object is in translational equilibrium and it's in rotational equilibrium. So if it's in both translational and rotational equilibrium, we just say it's in equilibrium. And if something is in equilibrium, the resultant force on it is zero, and the total moment or total torque about any point is zero. And the simplest case is a stationary object, and that's the most common thing you'll encounter. Now, let's use all that information with our first problem. I will read it through to you. A 5 kilogram mass suspended by 2 ropes, 4 meters long as shown. So look at the diagram. The top of the ropes are fastened to the ceiling with a gap of 3 meters between the tops of the ropes. Part A. Find the angle each rope makes with the vertical. So let's do that first. Pause the video and try answering part A for yourself. Pause now. And let's go through it. Well, let's draw the vertical in. Makes it easier. That vertical splits that 3 meter distance into 1.5 and 1.5 meters. And we want to know the angle the rope makes with the vertical. Call the angle theta. It's the same angle on either side because we've got an isosceles triangle. It's symmetrical about the vertical axis. How big is angle theta? Well, if you look at the diagram, you see you've got right angle triangles. If you look at one of them, the sine of angle theta is the opposite side over the hypotenuse. It's 1.5 over 4. Do the arithmetic. Theta is inverse sine. Sine minus 1, 0.375. Comes to 22.0 degrees. The question asked for gave data to 2 significant figures, so probably best to give the answer to 2 significant figures, 22 degrees. How about part B? Find the tension in each rope. And you told the value for G, 9.8 newtons per kilogram, same as meters per second squared. So pause and have a go at part B for yourself now. Let's go through this. What I'm going to do is redraw the diagram and just show the forces acting on that mass. So there's the object, the blue ball. There's the force acting downwards, that's the weight. There's the tension to the right and the tension to the left, and those tensions make an angle of 22 degrees to the vertical. So I can call the tension T. It's the same tension on either side because it's symmetrical. The left side is basically the same as the right side. So call the tension T. The weight is mg, 5 kilograms times 9.8 is 49 newtons. Now that's a very useful diagram just showing the forces on the object and a reference direction and angle. This sort of diagram has got a special name. It's called a free body diagram or free body force diagram, or sometimes just a force diagram. And it's a very useful thing to draw because it just makes it easier to think about the problem. You show the object and the forces on it and maybe some direction information. You don't show anything else. I'm not showing the ceiling, for example. It's irrelevant. You just want the forces. Now we're going to use our knowledge about equilibrium. The mass, 5 kilogram mass, is in translational equilibrium. It's not moving. So we know if we pick a direction that the upwards forces must exactly equal the downwards forces. The resultant is 0, so in a vertical direction, or any direction, but in a vertical direction, the forces one way are cancelled by the forces the other way. What are the upwards forces? Well, there's two of them. They're the components of the tension. T cos 22 from the left-hand rope and T cos 22 from the right-hand rope. That's the upward forces, and they must equal the downward forces. What's the downward forces? Well, there's only one. It's the weight, 49 newtons. So I can write this equation, which simplifies to 2 T cos 22 degrees equals 49. In fact, I could have written the second equation down straight away. It's pretty clear. All we've got to do is put the numbers in, rearrange T to get 49 over 2 cos 22, and when we work it out, it's 26 newtons. There we are. That's the problem done. We know the tension in each rope. It's 26 newtons in each rope. Just before we leave this, note it's symmetrical about the vertical axis. What about the sideways forces? If we thought about the horizontal forces, what would they be? Well, each horizontal component of tension is T sine 22. We've got T sine 22 acting to the left and T sine 22 acting to the right. These two components cancel. They're equal due to the symmetry. And when we get problems that are symmetrical like this, it simplifies the calculations quite a lot. We can take advantage of the symmetry, so we don't have to worry about the left and right hand components. Let's do another one, problem 2. It's a similar problem, but this time the angles are given to you. And in fact, they're angles to the horizontal, not angles to the vertical. A 5 kilogram mass suspended by 2 ropes is shown. Find the tension in each rope. Now the tensions won't be equal, it's not symmetrical. They'll have 2 different tensions. Given the value of G, your turn. Pause the video and see if you can do that for yourself. This is a bit messy. It's got some messy arithmetic and messy algebra in it, but it's not a difficult problem. Pause and try it. Let's go through it. The first thing we're going to do is draw a free body diagram and just show the forces acting on the object. That'll make it a bit easier to see what's happening. So I'm going to redraw this. Take a look at it. We've got tension. That rope is at 60 degrees to the horizontal. Tension here, that rope is 25 degrees to the horizontal. So our free body diagram can be drawn like this. There's an object. I've drawn a horizontal line in purple just for reference. And the forces on the object are the weight downwards. Turns out to be 49 newtons. T1, tension from the left-hand rope at an angle of 60 degrees to the horizontal. And T2, from the right-hand rope at 25 degrees to the horizontal. Now we've got 2 unknowns, so we're going to need 2 equations and do some simultaneous equation solving. How do we get the 2 equations? Well, we're going to start by what we call resolving horizontally. That means looking at the horizontal forces. This thing is in equilibrium, So in any direction, the components of the forces cancel. Whatever's acting to the left is cancelled by whatever's acting to the right. What force is acting to the left? Well, I hope you can see it's T1 cos 60. What force is acting to the right? It's T2 cos 25. So I can write down T1 cos 60 is T2 cos 25. I can rearrange that. T1 is T2 times cos 25 over cos 60. Put the numbers in to simplify it, and I get T1 is 1.813 times T2. Bit of an awkward number, but it's just a number. Notice I'm working to about 3 or 4 significant figures here as I work through. I want the final answer to be 2 significant figures probably, so I need to work to 3 or 4 significant figures for the intermediate steps to minimize rounding errors during working. So I've got an equation for T1 in terms of T2 by resolving horizontally, looking at the horizontal components. Let's do the same in a vertical direction. Let's consider the vertical forces. Because there's an equilibrium, we know the total up must be cancelled by the total down. Resolving vertically, I've got the equation here. Can you see where it comes from? The vertical component of T1 is T1 sine 60, upwards. The vertically upwards component of T2 is T2 sine 25. And if we add those together, that's the total upwards force. What's the downwards force? 49. So there's our equation. Let's put some numbers in. 0.866 T1's plus 0.422 T2 is 49. Now we've got to do the algebra. It's a bit messy, but it's not that hard. I know T1 is that number times T2. So instead of T1 in this equation, I'll replace T1 by 1.813 T2. So I get 0.866 times 1.813 T2 plus 0.4226 T2 equals 49. Now multiply those out, I get 1.57 T2 plus the 0.4226 T2, add those two T2 terms, 1.993 T2 is 49, so T2 is 49 over 1.993, comes to 24.6 newtons. To 2 significant figures, it's 25 newtons. So I know T2 is 25 newtons. How about T1? Well, T1 is 1.813 times T2. So all I've got to do is 1.813 times, don't use the rounded value, use 24.6, gives 44.6 newtons. Round that to 2 significant figures, you've got 45 newtons. So I said that rather fast. There's a lot of arithmetic there. If you pause the video, you can read through, or even better, do it for yourself if you didn't get the right answers. So pause and have a look carefully through that if you need to. Okay, well that's the end of part 1. In part 2, we'll simply continue with our problem solving. Thanks for watching.